Hello, are you aware that to test the validity of a formula, you can use dimensional homogeneity to do that? In my previous video, we analyzed that in physics, and that takes us to the subject physics. Takes us to the subject physics. Still looking at what? Dimensional homogeneity. And now we want to look at, take for example, the energy stored in a wire, okay, the relationship given to us. For example, if the energy stored in a wire, if the W, the energy stored in the wire is given as K, E, okay, KEA, then E raised to power X all over L is given with this relationship. The question says, find X, okay. If K is what? Constant. K is what? Constant. And then E is what? Young's modulus. And A is area. And the last one, which is E, is giving us what? Extension. So the question is, we should find X in this relationship. And if this L here is giving us what? The length, original length in the wire. So the relationship giving us this. I told you in the previous video, how do we solve questions like this in dimensional homogeneity? What we need to do is to represent each of these quantities with their what? Dimension. So what do? K is constant, so there's no need to work with K. Young modulus, what's the dimension of young modulus? Young modulus dimension is M L raised to power minus 1, T minus 2, raised to power minus 2. What is the dimension of area? Length times breadth, which will be N raised to power 2. What is the dimension of extension, which is E? And I told you anything that has to do with extension, radius, diameter, and length will take what? Capital letter L. And what is the dimension of length? That is also L in the dimension. So what's the next thing you need to do? The next thing you need to do is to now do what? Take this dimension and fix it into the equation relationship that we have. So what do you do now? W will be equals to what? K. Now what do you have as E? Young modulus. M L raised to power minus 1, T raised to power minus 2, okay? Times, what is the area? L2, L raised to power 2, and times, what is the extension? Just L, L raised to power what? X, all over what? What is the extension for length? L. So what do we do now? Because I want you to see clearly, I'm going to continue up, okay? Because I want you to see clearly. So I'm going to clean this part, okay? You've already seen the question. You've seen the question. So what do I do now? Since I've written this relationship, we already know what the relationship looks like. So I'll come here and I'm going to say W will be equals to what? K. Now, what is this now? W will be equals to what? K M raised to power what? M raised to power just 1. Okay? So that's it. Then L raised to power, what do we have? L raised to power minus 1. Okay? Then T raised to power what? T raised to power. Before we do T raised to power minus 2, let's work with this L. Okay? This L and this L. Now, what do we have now? To be L raised to power minus 1. Because of this base, we want to do what? We want to add their powers because the bases are the same. So you have L raised to power minus 1 and raised to power what? Plus 2. Okay. Times L raised to power X. Who know why we didn't add the X there? Because there is no need. Reason being that this X in the first place is standing on its own. It's not like we're looking for it. It's an unknown variable, so we don't know. So that's why we're living that way. All over what? All over this L. But look at what will happen now. What will happen is K raised to power M raised to power what? 1. Are you with me now? 1. Then you have L minus 1 plus 2 will give you minus 1. Is that taken? Okay? That will give you that will give you plus 1. Minus 1 plus 2 will give you 1. You understand? That's 2 minus 1. So it will give you 1 times n raised to power what? X all over this L. This thing is very simple and very straight. Don't forget this is W, and this W represents work. Quickly, work. What is the dimension of work? Work is Newton meter, which is joules. Is that also? What's Newton? Kilogram meter per second square times meter, which is the same thing as what? What's kilogram? We have what? We have M, okay? M times M is, this M here represent length, which will be n raised to power 2 and t raised to power minus 2. So here, that I've been writing work, I will change it to this dimension. Okay, so what do I do now? Quickly, let me clean this place so you can see quickly. Just follow me with the speed of light. Now, so what do I do? Anywhere I see this W, I replace it with this. It will become ML raised to power what? 2 and t raised to power minus 2 will be equals to K M raised to power 1, you understand? N raised to power 1, the L we calculated, times N raised to power X all over L. Now, I told you, this L can cancel this L, but not with the L raised to power X, because it has a variable. So this is the same thing as N raised to power 1. So what do we have now? We now have M, N raised to power 2, T raised to power minus 2 will be equals to K M L raised to power X. Since what we're looking for is X, therefore it will affect the dimension of L and the dimension of L. So all you need to do is to bring it out and say L raised to power 2 will be equals to L raised to power X. In the law of indices, the same base, therefore the powers can stand on their own. Cancel, cancel. Therefore, X is equals to 2. Therefore, your answer is what? 2. So in that relationship that was given, W is equals to K E raised to power X over L. This guy here is what? 2. That is what it is. I'd like you to subscribe. Follow me on Facebook and Instagram at Adobe Fikemba and on YouTube at Adobe Fikemba. See you in the next video. Thank you.